I'm pleased to introduce Professor Xiaoping Bao, who came to Purdue from postdoctoral studies at Berkeley, and before that, he did his PhD at the University of Wisconsin in the Department of Chemical and Biological Engineering. His area of expertise is controlled differentiation of stem cells, and during his time at Wisconsin, he made quite a name for himself by establishing a new and much more effective routes for control and differentiation of cardiomyocytes and other related cells from stem cell technology. He's won already numerous awards, and the most recent, which was just announced, is he won the College of Engineering's Early Career Award for research, and he also set the record, as far as I know, for the earliest NIH award by an assistant professor in our school, when his proposal that he wrote in his second year was an R01 was funded by the NIH. So please welcome me in welcoming Xiaoping Bao to the stage. Thank you.
That's that. Yeah, thank you, Sam, for the nice introduction. Okay. So it's my great pleasure today to share kind of my personal journey to associate professor and beyond. And I think I may just skip these because I already speak a little bit about my history. So, but I still want to get started with my personal life. So I was born and raised in Lanxi, Zhejiang province in China. So this is where the point? Oh, this is a very small town city in Zhejiang. I mean, small is a relatively word. It's a large, but this kind of in the middle of Zhejiang, close to Shanghai and the seashore, but still not directly in the seashore. And I never visited to any kind of north part of China before that. So then I picked kind of to study in Tsinghua, spent 4 years in Beijing, kind of north part of China, for my bachelor degree in chemical engineering. So this is kind of one of the oldest building in the campus, very beautiful. So afterwards, I even went further to kind of north to United States, to Madison, Wisconsin. And I spent about 5 years in Polytech lab, and just to be kind of a badger and study cardio tissue engineering in the lab. After that, I just kind of drove all the way down to the Bay Area, Berkeley, for my postdoc in joined the lab of David Shriver and Doug Clark. So Doug is the dean of the chemical engineering in Berkeley. So and I spent about 2 years as an American Heart Associate postdoc in the lab. And after that, I ended up being here at Purdue, building my own stem cell and immune engineering lab in the chemical engineering department. And I have a fantastic group. Now have kind of 2 postdoc, 6 PhD students. I only graduate 1 ARM. There are lots of kind of story there. One for many of them, a PhD student, kind of must out for various reasons. One example is during pandemic, one of my PhD students, he really want to be a real doctor. After a couple of years, so he went to MD program, and now in the IU. So there are many that happen. So that's why I only have 1 PhD graduate, but I do have lots of master students after that, and I have a couple undergrad as well. So for the funding source to support my group, for sure, major funding source like NSF, NIH, and I try very hard for the DoD Congress direct medical research support in between the NSF and NIH, and maybe 5 times, and even for now I don't get any. But in between, luckily for me, I got my pandemic boy during in 2022. So that's kind of some thing, and that's kind of about my a personal journey to academia. And what's my research area then? I just want to show you this kind of movie, this kind of the beating heart we made in the lab, and this kind of one major reason when I joined my PhD lab is to do on cardiovascular, because I don't think anyone can avoid like a really hot like a beating heart, right? So so do I by that time. So I just pick my PhD lab when I saw some of this cool video on the microscope when I pick my like advisor. So I'm still continue working a little bit, like make some effort in this field to trying to making like a broken heart. And the major reason I think many of you may aware of, like during a heart attack, you can like one single attack may kill millions of heart muscle cells, and they will instead like repair themselves, they will form tissue kind of scar or fibrosis in your tissue in heart. And unlike the skin like scar, you may get rid of eventually, but in heart it's not, and even worse. So there's a need for sure for the regenerative medicine, right? So that's where kind of the major breakthrough in the field come kind of the Nobel Prize winning technology, the reprogramming technology to make first the iPSCs from somatic cells, and these cells they can in general like form all kinds of cells, including heart muscle cells in your body, and these are human cells, and they are useful, and there are lots of clinical trial nowadays in different countries, and for sure in terms of heart tissue engineering, once you have these heart cells, you can make all kinds of application like disease modeling, cell therapy, or everything. And for my PhD or most of my like PhD studies, I kind of like printed this kind of different tree with a defined or simplified system to control and making all kinds of cardiac cells in the human heart. And that's kind of one major my PhD thesis work. And but one thing for that is you can make every single cell, but how you assembling this cell into a tissue or many like a cardiac organoid, that's another challenge in the field. So one thing in the field is mostly when you convince a cell fate transition from stem cell to useful cells, you use all these kind of chemicals, one example shown here, to control and manipulate the cell fate. But this kind of lack spatial like a control. You can only just a mixture of cell. So one way you can do that is using light, because light you can control the pattern more easily to achieve spatial resolution. So that's how like one thing I did in my post lab is to work and learn from another colleague in the lab to make some illumination device and to make a genetic tool that can spatially control the cardiac tissue. And I'm not going into too much detail, but one thing is if you check like this native heart tissue that we already have each individual component, but how you make that into the if you have some like a pattern with the light, we can make actually this inside the kind of the beating heart muscle troponin marker, and outside the epicardial that is the outer layer, and at least two layer with this kind of pattern too. And in 3D, you can also using similar approach to pattern kind of outer layer epicardial inside like endothelial and the cardiac mice are also heart muscle. So as a mini kind of cardiac tissue organ, we are trying to make more reproducible and with a chamber that are more mimicking the native heart tissue. And this kind of my ongoing NS career project on how we can engineer much better cardiovascular tissue engineer tools and organoids for disease modeling or transplantation application. So this is one of my like research area that I want to talk about related to my journey. And a second area is related to the immune engineering or cancer immunotherapy, where like the major reason is there are lots of cancer patients. Maybe you know somebody in your family or in your friends that kind of suffer from similar to me. My family have I feel people now get cancer. So one major motivation for me, I want to make some like a useful therapy by in my lab to kind of treat or change the how people like how patient of cancer get treated. So one promising like a therapy, cell therapy or nowadays it's called a chemical antigen receptor or short for CAR-T. So this is not the car that we drove, but that's the car how you can redrive the T cell or other immune cells to attack the cancer cells. And the pipeline to manufacturing this is shown here. When there's a patient, you go through the like a cell isolation, blood draw, and then enrich the target cell T cell, for example, and then transduce with lentiviral or other like approach, lipid nanoparticle, all these kind of tools. And after that, you enrich again, expand and enrich the CAR-T cells and put it back. So this is a clinical and or preclinical dominated manufacturing pipeline. So kind of combine my chemical engineer background and stem cell like background. This manufacturing, you will see lots of like challenges or defects in this. One of the very first is very expensive. One like a shot or one patient treatment can cost up to 500 like K or even more, depends on the location, and you will need a special like equipment for this. And there are a couple like technical challenges associated with the cell engineering. So with kind of stem cell, we want to make a new road, like to leverage the stem cell to make this manufacturing more like a universal or more off the shelf, and that's how we propose. Like start with the like a stem cell you engineer with like a Cas9 or many other like emerging genomic editing tools to put this CAR construct into these stem cells. So these stem cells are born with a CAR now. So that's where I put a Y to indicate that. And after that, you can convince using different like approach or platform to convince the stem cell to become every single cell in our blood or in circulation here. You can make it like CAR-T, CAR-B, or CAR natural killer or neutrophil. So that's kind of all kinds of cells. One cell line you can make all kinds of product, and with some other genomic editing you can make a kind of off-the-shelf product, and they are more homogeneous and have a better quality control usually, and this is more like off-the-shelf, so you don't have to wait the patient isolate the cell from that, and in theory you can have a product cryopreserved, and whenever a patient come you can sort and give them in like a weekly or like a less like than month like basis to achieve that. And this kind of how we want to like change the manufacturing pipeline in the cell manufacturing. And I'm not going to talk too much about a different story, but just one example, we kind of the first lab to make a CAR neutrophil. Neutrophil is one of the most like a dominant cell in our body that have the like whenever you have inflammation, you have more neutrophil. So we kind of use this to make that, and after engineering, you will see they are more powerful than any of the like CAR-NK or other cells, and similar thing in mouse study on the right, you can kill much more cells. The bottom line that CAR neutrophil compared to CAR-NK or other cells. And with these, we really want to again make a useful translational therapy. So we kind of collaborate with the Purdue like animal hospital to test. We've done this safety in like a beagle dog. So this is one of that. I think they named them Lucky. They all like a name. And after the experiment, this I think done. Almost 1.5 years ago, and all the dogs are safe, and this kind of similar as a kind of human patient measurement, all the safety like a pyramid, and after that, all these dogs I think are adopted by the real like they have like their own like home now for this dog. So we are trying to moving this to real kind of clinical trial in the animal like a hospital to just like a human, a few kind of cancer, they will develop natural like cancer as a human. So and Purdue Animal Hospital treat patient like a lot of these kind of patient every year or every month. So we are kind of collaborate to do that, and that's about like my two personal like trip in terms of research. And again, I want to make my like a translational research. I'm very motivated to do that. So we kind of patent a lot of technology and have a few more we are trying to make, and a couple of them are already licensed. And kind of I'm also serving as a part of like a CSO for a small company as near, and also option some of our stuff to NK Biosciences. And I'm kind of quote on the entrepreneurship because I'm not really doing any of that all by myself. But beyond at least like a period, I'm very interested to do some of my own stuff with new kind of technology. And with that, people always say it takes like a village to raise like a boy or like an assistant professor. So I think what I list and beyond are all my village at Purdue, and particularly my students and trainees. They are kind of real hammers at Purdue that kind of bully up my group. And for sure, there are lots of mentors like Sam Kim, for example, always like tell me not to worry about small things. Like where I kind of start, I worry about the money, right? I cannot take every coin or bit like, oh, how I spend that. But he always say, oh, like think longer and see what you get like 10 million to spend, right? So that's kind of question. And like John, my kind of faculty mentor who kind of always represent my case to the promotion, everything. And also like Enrico, like teaching me how to teach. We teach a couple classes. And Katie, who kind of coached me to like lecturing and writing a lot when I just get started. So I really benefit from that. And many other like kind of previous advice as well. We still keep in touch for some helpful stuff. And for sure, many fantastic like colleagues and collaborators. Just like for example, Ramki, who always stop in my office. We kind of have some quick chat on something, and many like other colleagues that I like collaborate or just have lunch, have this kind of small coffee to discuss project and funding and research, or even like mentoring or being a faculty, and many others. And also for sure like it's funding source that make all this kind of like a financial support for my research. And lastly, a personal thank you message for my like family, my wife Jay, and also my cute boy like Austin, 3 years, almost 3 years now. So, and I will stop here, and I will be happy to take any question.
Okay, questions, and I have the microphone. So. I'm sure there must be lots of questions. Oh, Dr. Ramki.
Xiaoping, how important is it for you to be involved with clinical studies in your research on immunology, treatment of cancer, for instance?
I think for my like pre-tenure, I think it's not as that important because most of my research is on like a basic or preclinical, and Purdue have all these facility and collaborate. We even have very good animal hospital to do that. But beyond this, if I want to translate to real clinical trial, I have to for sure collaborate in Indiana University School of Medicine or other hospital, right, to do this, to collaborate, get funding to work on this trial, right. So I think for sure in my like the next 5 or 10 years, it's kind of more important for me. Yeah.
Any other questions in the back there? Well, I have a kind of off-the-wall question first, and then some serious questions. Are you familiar with this child psychology paper that just came out that said it's a very bad idea for a child to grow up in a city with the same name as himself or herself. Have you heard that theory?
No.
Yeah. Well, it turns out it's very true. So I think Austin will be much happier in Austin, Texas. So,
I see.
serious question. Same question I asked the previous speaker.
Yeah.
So now with inflation, it's $10 million. So if a philanthropist says, here's $10 million, what's your best idea that you don't really want to haggle through peer review and so on, just get it done, what would you do?
Yeah, one thing that we just have proposed supplement to COE Blue Sky that I think one example is all this treatment is really expensive for like cancer therapy. We want to do an institute just like an in-house like a dialysis. What if we can do at home with like a device? You take a patient blood and coming out you have the product go back. So that's something we want to do if possible.
Okay. How about the distance to medical? I think it's touched upon that. We don't have a medical campus here. Now, you were at Berkeley as a postdoc, and Wisconsin, of course, has a medical school right on campus. Berkeley does not. What are your thoughts about the importance of having a medical school right on campus versus longer distance collaborations?
I think the overall environment, if you have a medical school, you will have a much more like people around it to work on the same, for example, stem cell or like related to my research. So you will have more directly related like research interest to collaborate and work as a big team. Without like medical school, you may, for example, when I started in Purdue, who ever work on human proven stem cell, maybe only 2 or 3 real work on that. Yes. But now we have, even without a medical school, we have more. So, but if there's a medical school, this kind of research, you will have much more like a collaborate, larger pool for that. So I think in that wise, you may have more co-develop ideas or collaboration more. Yeah.
Okay. And the final question, this will be my last question. I'm sure there will be questions from others. Now that you have tenure and don't have to worry about what the senior faculty think, do you think the name of the school should be changed from chemical engineering to add some bio-related word? So what is your honest opinion on that?
I'm personally fine with the name because I think people know mostly, even my own research is not where you are afraid, what's your afraid. It's all mostly your work, right? So people will not check, you are in chemistry, But you're being very polite, but in a secret ballot, would you vote to keep the name or change the name to add bio? In a secret ballot, how would you vote? No, not secret.
That's not secret.
Yeah, I will vote yes then.
You vote against it?
Yes, yeah.
I'm surprised. Okay.
I vote yes.
You vote yes. You vote yes to change the name. Okay, very good. Other questions? I'm sure my chemical engineering colleagues must have questions. Fabio, you must have a question.
I know about energy.
Okay. Oh, okay. Letian, yes.
Yeah.
You go first. You go first.
So, Xiaoping, one of the claims made that leads to cancer is errors in transcriptional regulation. Given that, what would be your approach to dealing with that? I mean, how do you discover transcriptional regulation and the consequences of it?
My work, as I mentioned, focuses on more cellular level instead of the transcription level. But that's for sure really important. That's how we, usually people design the CAR to target the mutation, right? And the special unique marker or antigen in the cancer, that's all related to translation, right? So I personally don't have that expertise or funding of people to work on that. But for sure, that's very interesting. If we can discover, for example, new antigen for CAR design or to better design the cell therapy.
That's an area we can collaborate.
Yeah.
It looks good.
Yeah. Congratulations, Xiaoping. So my question is, now you have tenure, My question is, I know you can multitask, but I want to hear your opinion in the next, say, 5-10 years. Which area you want to more focus on? Keep doing your own research, teaching, or more entrepreneurship, doing a company, commercialization, or more administration service? Which area you want to expand more?
I think one still keep focus on research, but I'm also interested in expanding in the entrepreneurship. Like for example, to establish some a kind of small company to see if we can push some of the patent technology to kind of entrepreneurship or to real application for that. And but still focus on mostly on discovering new technology side after tenure. Yeah.
Okay, let's thank all three speakers. Congratulations.
Thank you.